Okay, we are back to silicon carbide and gallium nitride device session. And the next speaker is Suhail Khan from 2.6, and he will talk about integrated wide-bandgap technology at the center of clean energy revolution. Please.
Hello, good afternoon. It's difficult right after lunch, but we'll see that if I can get your attention. Many of you may not, at least I experienced that. Even my friend Victor hardly mentioned 2.6 in his chat about what's going on in silicon carbide and how much work and effort we have put in. So I would kind of touch on what it means from being in Europe. I have to talk about the environment, how we are going to contribute, and then also what we are bringing to this discontinuity, which we think is the third wave in the semiconductor business. Let's see how it goes up and down. Just a quick one, that name, it comes from the periodic table. It's basically started with the material base, and we are one of the largest compound semiconductor companies vertically integrated, all the way from fab to manufacturing. And different from all the big guys who came from silicon world. So we are coming from the compound side into the wide bandgap material. It's just to give you idea that we are 22,000 people in the company all over, which also tells you that what we design, we like to produce also. So that's why you see all the resources and the people. So as I mentioned, that we came from the compound semi background. And if you look at that, we have the presence in almost everywhere with fabrication, back-end, materials, and that's the basis on which we are moving up the value chain. And I think it was Victor who said that 70% of the value is in the substrate and the most difficult part. And I am very pleased to say that to be really, there are only two viable suppliers of that high quality substrate. It is Wolfspeed and us, and rest are trying to be. So what's happening is that how the demand of the energy is coming. That if we look at that the growth in the energy demand coming both from the developed as well as the underdeveloped world. But the biggest problem is even with all these sources which are coming, the conversion ratio is still not very good. So there is still a 2x gap between the demand and what can be delivered. So one of the very critical things what this technology brings is that improvement in that conversion ratio so that we can get this to maximum number of people. And so while the electrification, we had different revolutions, different decades, I think this one and the next one is the electrification of any and everything. So just to give you the idea what that means, that we look at what's the demand forecast and the usage. And if this is the primary energy source with the demand, which you can see. And if we can go to silicon carbide, you can see we can save about 3 to 10% that means there is another 10% of the people who will have the ability to benefit from this. Another very important thing, if you look at the CO2 emissions, that basically you save anywhere from 30 to 65 megatons of CO2. Do you know what that translates to? 1 gigawatt coal-powered station that will consume. So basically this you can save about 4 to 8 of those coal-powered power stations by going to this technology. So not only from the saving standpoint, but also from creating a much cleaner environment. So also other thing I heard, somebody said that lithium batteries are going in price up. There is more need for more silicon carbide. So music to my ears and others, that means we can charge more. So that price delta doesn't need to be that 20%, it can be a lot more. Because look at what we are delivering. Huge market. It's thanks to you all, they are here. So we think we think it is conservative. We think the vector is going to be even higher than what's projected here. So why? Because I think all of you have heard, all of you know what's driving the demand, that many of you shared your products. I will touch upon a little bit. I'm not going to go into the product detail because you guys know the products or you can see it from the data sheets. So there is, the demand drivers are very strong. So whether they come from the EV side, whether they come from the green energy side, that solar, wind, people are not really underestimating the opportunity in wind. And especially that's where a lot of this conversion ratio is going to become very important and critical, and people will be needing the devices at not only 1.2, 1.7, 3.3 kV. So there is going to be more and more of those demands which we are going to see. So given that, what we have decided is that, as I said, we are the people at the ground floor. So we spend 20, 25 years in working on this material, the difficult material, as everyone knows, difficult to control defects, difficult to have flatness, difficult to address the growth and the size. So all those issues we have been working on this thing, and that's the baseline on which we are moving up the food chain. Very pleased to say that we acquired Escatron, which is a local company, which I'm so happy and proud that they are part of our team, that they can offer this 3D SCAPE, which will be very important and critical as the voltage goes up. So we have one of the leading API companies as a part of our team. And then, we had designers. We could go and design the transistor. I started in the 80s with that, so I'm going back there. But the issue is not that you can design. Issue is, again, the knowledge and the experience, the ability to deliver a high reliability product, which has been tested and used. So we made the partnership with GE. And GE is in this business longer than anybody else. And those are the partnership and the devices working with them, which we have already brought to the market. We are sampling 1200 volt MOSFET, which meets ACQ 101, and also not 175 degree, 200 degree. Under all conditions, we will guarantee. It's not moving. Okay. So just to share with you where we started and where we are. We were the first one. In 150, the Wolf speed was ahead. In 200, we were ahead. And we delivered the first 200 millimeter samples. We are in very high production, high volume production for 150, and we are already also sampling the 200 millimeter substrates. Why this doesn't? Okay, so to give you a little bit more of the pictorial view, we grow crystals. And it's a very stable platform. From there, the substrates, and then, as I said, we have added the API capability. So we will be providing our customers substrates as well as API wafers. And then, as I said, we are moving up to offer the MOSFET, and then also working with GE in delivering the modules, which will be as I heard earlier, that modules will make a big difference in the performance and a particular design. And there are many different types of modules which we plan to offer. And one other thing is that we are very open to adopting and going where the talent and the skill set is. For modules, we know it's in Europe, so we are putting the design center in Europe. It's already here, who is already working in designing various modules. So basically, what you have is a full chain from the base materials all the way to either bare die, to packaged devices, or to modules. Why? You say, why not? You were good in one thing. Why not just stick with it? There is always, you have to think about not only from technology, but also from your ability to make a market happen. And also there should be a benefit to your investors who are investing all that money. By having this vertical integration and controlling this, we eliminate the middle person's markup. So there are no double margin stacking happening. So if just somebody, if I can deliver silicon wafer versus just somebody who buys the substrate from either us or from Wolfspeed and then goes to the market. So this is a difference. Similar thing in every aspect, that basically what this is going to do is that the thing you guys talked about, that the silicon to silicon carbide, that margin needs to collapse. And the way it will collapse is by having this ability to produce more. So, so I think that the value which we are delivering is already unquestioned. Everyone is on the same page that a system level savings from any and everywhere you look at, this is a big benefit. And then you bring this technology, it's the early stage of silicon. That's what I experienced in my early 80s. And now we are experiencing with the silicon carbide, and we will see the same uplift. So what we have decided, we are going to spend $1 billion in growing this capability. And I will also make the statement, which we have made. We will produce 1 million substrates because the demand is so much that we can, if the capacity is there, we can ship double. So we are making huge investments to increase our capability to produce these substrates. We are added the EPI capability both in US and Kista. So Kista will be adding more reactors and able to support the European market. So people even this is an industry where competition, cooperation, partnership all works together. So even the big guys don't want to be single source. So you can basically use 20% of the EPI wafers from us. And then I touched upon the 3D SiC, which is the special technology and capability which Escatron worked for a long period of time, and we will see the benefits of that. And then what I mentioned is that the maximum growth we plan to do is in Eastern Pennsylvania. So just to sum it up, that I think I don't think anyone in this room will disagree that it's a very fundamental base technology for this next change in how we live and how the electrification of the universe will happen. That the applications that we feel, I heard a lot about GaN, and GaN is a good technology capability, but it will all coexist. So 650 and above, it will be tough and difficult for GaN to offer the same capability as what can be offered with silicon carbide. With the investments and the solution, hopefully, Victor will add our name in most of his charts that as part of the Power America, that a company which is bringing a next generation of solutions to the marketplace. So any questions I can answer? Yes.
Time for questions. Yes, please.
Hi, Simon Price from Exawatt. I'm just wondering if you could give us some guidance on your current wafer capacity in 6-inch equivalent.
You cannot.
Simple question, simple answer. Thank you.
You want to answer?
My question is, with respect to fabrication, do you view yourself as a fabless company going out to a foundry, or do you plan to have your own silicon carbide device fabrication facilities? I know you mentioned Easton, which is actually a very nice part of the country. I used to work nearby.
Yeah.
And I know there you got the substrates and you're basically scaling up the production of the substrates. But for the device itself, do you plan to acquire a fab where you make your device and you'll be an IDM, or will you be using the foundry model going outside for your fabrication, or maybe both?
I think currently, as you know, we are using a foundry. As we look out based upon our customer engagements, we will make the appropriate decision. So it's not one way or the other. As I said, very pragmatic view of if we are very much customer driven. So if and as you know, as I said, we have lots of fabs in compound semi area. So fab is nothing new to us. Just to give you guys an idea that a few years ago, I can make a public statement because it's out. This company approached us that they wanted to have the VCSELs for both front and back. And we were able to bring up the capacity in Warren, New Jersey, where we have shipped hundreds of millions of those products, which anyone who has an iPhone, there are anywhere from 3 to 5 VCSEL devices in each phone.
And one more big question. With respect to the 200 millimeter wafer, there's all these fabs that do 200 millimeters. They're waiting for the suppliers to come online so they can start processing 200 millimeter silicon carbide. Do you have a time frame that, I know in 2015 you did your first demonstration. Do you have a time frame for when you're going to go to market with 200 millimeters? And are you going to be the first?
No, I think in production, because they have the fab, that people are not ready with their fabs. So we are ready, but I think customers are still going through the process of bringing the fabs up. I think the only fab which is ready is Wolfspeed. Yes.
Maybe I saw wrong in the slide 9 where there were your timeline.
Yeah.
I saw 6H. Are you working on 6H?
Yes. We are the largest supplier of semi-insulating substrates. So we are shipping both 100 and 150. Yeah.
What about 3C? Are you in your plan?
We are looking into all those basic capabilities, technologies, anything which has a potential to impact the business, we need to be in it. We need to analyze and see. But the main focus is to provide our customers high quality, high reliability, high volume product at a competitive price.
Let's thank the speaker again, and we are moving to the next. So next presentation will be done by Martin Domey from onsemi, and it's about performance and reliability of the new generation of MOSFETs.
Thank you for the nice introduction. So, can you hear me well? Not so. Okay, so I'll talk today about the performance and reliability of onsemi's new generation M3 1200 volt silicon carbide MOSFETs. So first I'll give an onsemi corporate overview, and I'll talk a little bit about our MOSFET, new generation, where I will highlight performance, a little bit about the body diode behavior and reliability. the summary. Yeah, so on semi, it's not so well known. Still, I think in silicon carbide come a little bit from the low power range. Have a revenue of $6.7 billion a year, headquartered in Phoenix, and 33,000 employees worldwide. So it's a company that has grown through acquisition. So we have 43 design centers in 19 countries. It's very widespread. And we have manufacturing also in many countries. So actually even 72 billion units shipped, including of course very many small chips like small silicon MOSFETs. And we have the front-end wafer or device processing fabs, 4 of them in the US. We have one in Bucheon, Korea, where we do the silicon carbide. And then we have also in Japan. And we are also now in materials for silicon carbide, also crystal growth and wafering, and back-end facilities in several countries, especially China, for silicon carbide, but also a little bit in Malaysia and Vietnam. This we all know here that silicon carbide brings a lot of use in the electric powertrain for an electric car. You can argue if it's 8% increased range, but significantly increased range. That's why the silicon carbide MOSFETs are in the Tesla and coming in other electric cars today, in the powertrain and also in the onboard chargers. This is a little bit about the onsemi here. We have now substrate technology in the company through the GTAT acquisition last year. We have the crystal growth and the wafering internally. That we have silicon. onsemi has been doing silicon wafers in the Czech Republic, so we have this background technology also now working out for silicon carbide, and we have the planar MOSFETs working a little bit also on trench MOSFETs for the future. And regarding the wafer size, we have always been in 150 millimeter from the start in production. Now we are looking into the 200 millimeter, preparing to migrate to that also. And the devices, we have diodes and MOSFETs, different packages, and then we have also modules. I will not talk much about here. So the applications driving, as mentioned, we have the industrial applications, PV inverters, UPS, energy storage, and the industrial for us also involves the charging infrastructure for electric cars that goes into the industrial. So very much is driven by automotive, even some of the industrial. And then in the car, it's the drivetrain and the traction inverter also. And the packages we have, discretes, are TO247 in 3-lead, 4-lead, and also D2PAK 7-lead. And we are now announcing the M3S silicon carbide MOSFETs that gives up to 20% power loss reduction compared to industry-leading competition as evaluated by our apps teams. And we have also the diodes, and regarding modules, we have hybrid modules that have silicon IGBTs with silicon carbide diodes, and also full SiC modules, either including diodes or just MOSFETs. This is a little picture here of the VE track module that's popular for automotive. And we don't have the modules on our website. You can contact our sales if you're interested in modules, but the discrete packages you can find in our website. This is a little overview of the different MOSFETs we have today. So our first generation, the M1 1200 volt, was released in 2018, 2019. There we have 20, 40, 80, 160 milliohm released. And for 1700 volt, we have now also the M1 released in 28 milliohm. The second generation we made, called M2, was only for 900 and 650 volt. And there we have a number of different milliohm ratings that are now all released. And this is actually where we have the main production and sales now is in the, for automotive, these lower voltages here. And now we have released also the newest technology, the M3, M3S for switching in 22 milliohm, and we have also one that's better suited for traction with 13 milliohm, a little better short circuit capability. So this is just same overview of the products. We have the TO47 3-lead, 4-lead, and D2PAC 7-lead. And the black ones are here, the ones that are released for the M3 technology, the M3S for 22 milliohm here, and the M3P more for traction for 14 milliohm. And then there are more smaller, higher milliohm dies coming. So here are some numbers in the comparison. Here we have, we're comparing dies that have the same milliohm rating. This is important when looking into the switching losses. So the M1 is 20 milliohm here, had 20 volt operation, and now in the M3 we have gone to 18 volt operation, which is common in the industry, can also work at 15 volt, and here we have competitor A. So here we can see that we have reduced the figure of merit, RDS-on times QG by some 31%, and RDS-on times EOSS by 44% compared to the M1. And also favorable results compared to competitor A here of the same milliohm rating. This picture, I think, illustrates quite well silicon carbide. You often say that it's much more expensive than silicon, but when you look at the die area that you use for the same applications, yeah, it's not clear. Silicon carbide is not that more expensive than silicon. So here we can see the Fairchild, or then later on semi, silicon technologies, field stop 3 IGBT plus a diode. You can replace that by our M1 silicon carbide MOSFET, which is much smaller, and now the M3 even smaller. So since the chips are getting smaller and smaller, also cost of silicon carbide is improving. Plus, of course, the capacitance, which is getting smaller, almost proportional to chip size. So when going from the M1 to the M3 1200 volt silicon carbide MOSFET, what we have done is mainly to reduce the cell pitch significantly, improving manufacturing to be able to make a smaller cell pitch, and a little bit of channel area engineering, and we have gone to a little bit thinner wafers also to get lower RSP. So here are some plots with comparison of the turn-on switching performance for 800 volt, 40 amp, and then a gate resistor 4.7 ohm, 18 to -3 volt switching at room temp with the body diode in the upper side. And then we see we have a significant reduction in M3S compared to M1, compared also to competitor A. And at 150C, we see a little bit higher losses, but still the same trend here. The factor that gives the improvement is better transconductance of the M3S compared to M1, plus a smaller capacitance of the die. And as you see, we have a little bit higher ion losses at higher temperature, and can wonder why do we have that? We should have capacitive currents in the MOSFET, but we have also a little bit of losses due to the body diode reverse recovery. That is the reason why we get a little bit higher ion at the higher temperature compared to room temp. Here is a comparison. Now we have instead the JBS diode as freewheeling diode. Here is the same ion comparison with the JBS diode. And to the right is EOF, where we also have a clear reduction of the M3S compared to M1 and competitor A. And the low gate charge is a key factor for low EOF losses. And here is a little, we look into the reverse recovery of the body diode. It's very good to compare it at room temp to left graph to high temperature, 150C to the right. If we have a purely capacitive current, then it should be just the same. But typically we see a little bit higher reverse recovery for the body diode at the high temperature for all of the MOSFETs. Here we have also the Schottky barrier diode included. And we can see that our M3S is a little bit better than the M1 technology here in both room temp and high temp. So we are currently, or we have looked into a little bit what is really rolling this body diode recovery, how can it be controlled? And one key thing to study the body diode is the forward IV characteristics. And an interesting thing is that, you know, silicon carbide PN diode at room temperature, it has a built-in potential of 2.8 volts. But when we have VGS 0 volt applied here, you can see that the body diode starts conducting already at 2 volts or less than 2 volts. So we have clearly a channel conduction, so we can use the MOSFET channel to conduct current as the body diode is forward conducting, and that is helpful. And in the M3 technology, you can see when we go to -3, -5 volt, we have deactivated the PN junction diode a little bit. So we get a little bit higher forward voltage drop, but on the other hand, we get less carrier plasma injection. And this is due to more efficient channel conduction. So with channel conduction of the body diode, we don't have the same injection efficiency of the PN junction. So it can save some switching losses for the body diode. Here we can see that comparing the M3S, we have a little bit of temperature dependence here due to the reduction of built-in potential, also for channel conduction when going to 150C. But for M1, we have more temperature dependence. Yeah. So we will study this in more detail. Okay, now we come to the reliability part. So gate oxide reliability. It's often argued that silicon carbide gate oxides are not as strong as silicon gate oxides. There are many traps and things. But our experience after a lot of study is that the gate oxide reliability is really on par with that for silicon power MOSFETs. And one easy way we have to evaluate gate oxide reliability or look for weak spots in a die, monitor quality, that is to just force a current through the gate until we get a failure. And then we often use 5 milliamp per centimeter square is convenient. Then the gate oxide goes into breakdown, starts tunneling. We measure the current until it fails. And here we can see results for NMOS capacitors compared with bin 1 product dies that pass the sort. And we can see that the bin 1 product dies are as good or possibly even better than the MOS capacitors because we can sort out some areas with defects in the sort program. And interesting is that we test silicon MOSFET product manufactured in the same fab, and it's a bit lower in gate charge, can depend on a little bit different tunneling, but it has also a little bit of a tail. So all in all, we think the gate oxide breakdown in a silicon carbide MOSFET behaves just like on silicon and is controlled by the gate oxide the silicon dioxide dielectric itself. Yeah. Okay, so this is something we do to monitor the quality, look for potential weak spots in the MOSFET. Then important for the gate oxide lifetime is the time to fail. We do time to failure measurements here. These run for a very long time. Here we have the M3 from 30.5 up to 35.5 volts here. Monitor current versus time until we get failure. And we can see that we start to get electron trapping after a charge of about 1 coulomb per centimeter square here. And yeah, we can then see like a critical charge to failure here. And from this, we can determine the time to failure versus voltage. And we extract, given the distribution here, we can extract the lifetime with 5 ppm. So it's about 20 years, 5 ppm lifetime at max rating 22 volts here. Yeah. And these tests take long time, up to 16 weeks here in the furnace. And then we have, as mentioned before, also the reliability at high voltage. And this is some nice work by Lichtenwallner at Cree, putting a high bias on the devices, measuring until failure due to gate oxide breakdown in the JFET region. Here is a picture from Kimoto explaining the reason for this. In silicon carbide, we have a high field, 10 times higher than silicon. And then we get also a higher field in the gate oxide in the JFET region due to this ratio of dielectric constants. This is difficult to do lifetime testing because you have to be really close to breakdown, and if you test into breakdown, then you may start to influence the characteristics. So yeah, also very time consuming. One interesting finding I want to share here that I think is not so spread is in the testing we have limited the current with fuses here, so we should not get so much damage, so we can see the failure analysis in detail. And we tested and we did cross sections. Here is one that does not intersect with our active cells, so therefore I'm allowed to show it here. And interestingly, we see a dislocation in the silicon carbide just below or beside the gate oxide damage that happened. I should say this is for a device we designed deliberately to have a wide JFET region to get failures, to see a little bit where the limit is for failures in HTRB. And we did this a number of times, and we have found dislocations just next to the failure, and that can of course not be a coincidence. And then we found the paper by ST co-workers from 2020 describing the same thing. So we think what happens here is that at 1200 volt there is some avalanche multiplication in the dislocation, creating some energetic holes that accelerate the failure. Yeah. So anyway, have to design the JFET with low enough field, and also test large areas of devices to be sure that some have defects also in the JFET region. So here is an example for the M1 MOSFET. We do not yet have the long, we have qualified M3 with 1000 hours, but we do not have the time resolved data yet. But this is for the M1 MOSFET we tested up to 1400 volts. We had one failure out of 40 at 1400 volts. So yeah, looks like we're good enough here. No failures were 1300, 1350 volt, which is still pretty accelerated. Yeah. And finally, on the gate oxide stability, or MOSFET stability, one thing I want to highlight is the threshold voltage stability. We have shown before DC bias stress threshold voltage stability, so we'll not show that today. That's quite well established. There is some trapping, detrapping of electrons and holes. But more recently discovered drift is during transient VGS stress, even called bipolar stress, from negative to positive VGS by a gate driver. There is a shift in threshold voltage reported in AppNote by Infineon and studied also by some Chinese researchers. And here we have done some accelerated testing. We have gone to used -8 volt here, which is higher than needed in than recommended in application. And what we do is we run stress at 700 kilohertz between -8 and 18 volt. And then we interrupt and do a parametric measurement of threshold voltage to the left here, and RDS on to the right. And here is our M1 and the M3 device, and here is the competitor A. And here we can see that according to the publication by Salman from Infineon, 111 is the whole lifetime for electric vehicle application, traction inverter. There is good even with this accelerated voltage, and for PV inverters it's important to test really long times. But this is more accelerated, so we think the M3 looks good, and also, yeah, increase in RDS on is really small. But this is an important test to carry out, and it's quite easy because it requires only the gate driver. So in summary, yeah, onsemi is today getting vertically integrated. We have our own substrates and wafering technology and ramping the production a lot. Yeah. Automotive is the big driving market. We releasing the new M3 1200 volt MOSFET with significant reductions in RSP and the switching losses and body diode recovery improved. And then discussed a little bit the reliability here also. Okay, thank you for your attention.
Now we open for questions. Yeah, Victor.
Thanks for your very good presentation. My question is, what are onsemi's plans for 3.3, 6.5, and 10 kV? I know this huge EV commercial opportunity that's in the lower voltages has most companies focusing on that. But what is your strategic plan for the grid and other applications that require high voltage?
I would say currently we have no near-term plan for the very high voltages, like 3.3 kilovolt and up. And I think to accomplish that, we would need some kind, maybe partner with the module technology. onsemi has not experience of these customers in the high voltage, but so I cannot give I cannot tell any timeline for this. The focus is on the voltage rating 650 to 1700 volt currently.
Here's the question.
The question is regarding the short circuit capability that you have had between generation 2 and generation 3, M2, M3. Have you had any improvement?
No, the M3S is developed for high efficiency, so short circuit capability is not as large as in the M1 that has a higher RSP. This is something we're working on, and the M3P that we're releasing has better short circuit capability, so that at the expense of RSP, we have one product offering here with better short circuit capability. But that's on the order of 2 microseconds.
Just one short question. Do you think that still bipolar degradation is an issue in your products?
Sorry?
Bipolar degradation is an issue in your products?
We have that ISiCPEAW paper, and we're looking into that also. So we did actually even binning package devices with different numbers of VPDs. And our conclusion was that under reasonably DC current stress with reasonable current densities, we see very little RDS(on) increase. But going to extremely high current densities, we do see significant bipolar degradation. We expect this in any MOSFET. But for regular use, we see very little.
Okay, let's thank the speaker and move to the next. So the next presentation will be given by Gabriele Bellocci from STE, and that's about method of control of barrier height in silicon carbide Schottky diodes.
Yes. Thanks for the introduction. I'm Gabriele Bellocchi and work in the R&D group of silicon carbide in ST based in Catania, so Sicily, for the audience. So basically, all this morning we had a lot of application on silicon carbide MOSFET. So I just go very quickly here. We can find the silicon carbide MOSFET in smart industry, smart driving on OBC and so on, smart home and city like telecommunication and energy transmission. And for sure, because of this huge application and huge market, ST cannot be there in the field. So we start with our G1 silicon carbide MOSFET, which has a very optimized air-on and temperature junction, and we span for 1.2 to 1.7 kV. Then we moved to develop the Gen 2, in which the air-on and the QG is very balanced, and we open the way for automotive application. And then now we are in the market with Gen 3 that has very high frequency work, so it can span again the application, and we have a very huge voltage range. But we are not stopped to develop, so from our Gen 3, we are going to another Gen 4 that has a lower area-on of about 15%, and he has an integration of current temperature sensors. So again, we would like to develop our MOSFET for wider application and the Gen 5. And we are looking also to the Gen 5, and the most features is that, the most important feature is that it will be developed on 8-inch. But we are not just looking on silicon carbide MOSFET, but also on silicon carbide diodes, and this because diodes has a very huge field of application. Basically, we can find diodes everywhere. And for now, we have two range of tension, of voltage, so 650, and in this ensemble, we have two different products, one that show low VF and another with high surge capability, and we qualify our product both for automotive and industrial, spanning from 2 amp to 40 amp. And then we have also 1.2 kV, and again for qualified with automotive grade and industrial application, spanning from 2 to 40 amp. But again, for our silicon carbide diodes, research and development is really in the field. So the new generation for the 650, where Victor said that is the battlefield at the end of the day, we tried really to improve the performance, lower the forward voltage from 1.75, we obtained 1.45, and we increase also the surge capability of a double value. And also for 1.2 kilovolts, we shift our VHF of 300 millivolts, so increasing again the efficiency of our device. But as you know, to obtain all these results, we have to play with different technology changes. One of that is the barrier height, because in silicon carbide, basically in diodes, JBS1 that we are talking about, silicon, the Schottky barrier height plays a key role. So what I would like to give you, there is a shift, all right, I will tell you. What I would like to give you is an overview of how, which approach we used. We can play by changing the materials, that it should be this circle here, should be there. The material is here, the design, or the process. Basically, if we change one of these parameters, we can modulate our Schottky barrier height. But what is really interesting, at least to me, is the combination of these three approaches that we can play at the same time together and see what happens. And I will show you four research that we are developing now based on this combination of this approach. So the first is, let's consider to change my materials. So basically our JBS diodes are made with titanium, 80 nanometer thick, as a Schottky barrier. We explore other metals. One of that is WC, so tungsten carbide. And just putting with the same condition, with the same process, the tungsten carbide on top of our silicon carbide wafer, we obtain a lower of our Schottky barrier from 1.2, that is the typical value of titanium Schottky barrier height, to 1.1. And lower Schottky barrier height means lower VHF at the end of the day. And if we look to the ideality factor, it doesn't change. And so that means that the quality of my Schottky contact is really good. And okay, this is something that we can imagine because each material has its work function, and if I couple it with my semiconductor, then depends also the Fermi level, I can modulate the Schottky barrier height. But we combine not just the materials, but also the process, so we start to anneal my materials, and again, I observed a shift in the left side of the plot. That means another gain of 50 millivolts in 50 millielectron volts in Schottky barrier height. And that means at the end of the day, as I said, a gain in efficiency. And if I plot, this is what I said. So the Schottky barrier height as a function of the temperature. And for these materials, we observe also a shift down, a slight shift down of the ideality factor. That means that these new materials give us not only a lower barrier, but also a better shock-T contact. So it is really interesting. Another approach that we are studying is combine the pinching effect with different epi. Okay, the pinching effect is basically how JBS works. So what we have done is basically change the shock-T area by changing the distance between the two P plus implants. And we combine this, it is well known, with different epi. So I sketch here epi 1, we can consider with low doping epi. Epi 1 star, in which I dope this epi by implantation. So it's higher, it shows higher doping than epi 1. And then I also combine the different pitch with an epi 2 that has higher doping than epi 1, that is grown on epi 1. And again, I implant epi 2 and I double implant epi 2 and see what happens. So if I here the top part of the plot is the shock-T barrier high, here is the VF. So starting from the typical, so the low doping, I can see that my pitch modulates the VF as expected because I just have a lower shock-T area, so the VF increase. And as expected, the shock-T barrier height doesn't change because it depends by the surface. Again, if I put my stack epi 1 and epi 2, that again epi 2 has higher doping level than epi 1, the shock-T barrier height fall down as expected because it has a higher doping, and I can modulate the VF. But you can see that VF doesn't feel so much the doping of the epi 2. Basically, are the same value. Okay, there is just a slight shift down, but it's the same value. But if I took the epi 1 and I doped by implantation, so I just changed the doping but in a different way, again, the barrier height, it remained the same, but the VF dropped down abruptly. And again, with pinching effect, I can modulate my VF. And following this, with epi 2, the barrier height fall down because the doping of epi 2, and then by the channeling, by the implantation, also the VF is very low. And if I double implant the epi 2, again, I observe a drop down of the VF. But what is interesting to me is that I can I can span from 0.74 as VF at 1 milliamp to 0.66. So a quite huge range in a very controlled way. So, but when we design our devices, we are interested not just in the VF, but also in the leakage. So we correlate, we plot in a correlation plot the leakage and the VF. And from this correlation plot, we can get some interesting information that this area of the plot, in this area of the plot fall the point in which there is no implant. And you can see that the leakage, it doesn't affect so much from the pinching, while the VF changed a lot from, thanks to the pinching. In this area here, we can find the points that has implant in which the pinching effect play a key role to control the leakage, but not so much in the VF. And from this point to this point, we observe a very nice curve in which we can find all this point here, and this means that when I have the requirement for marketing, for example, okay, marketing say every time that I have to be the best in leakage and VF, but this is not the case. But if I would like to find a compromise, this to me is really, really interesting because I can basically continuous span from the optimization of the leakage and the optimization of the VF. Another approach that we used is just starting from our traditional device that I said you, this 4H SiC, 8 nanometers of titanium, and there's aluminum compound just for the contact, and we change the titanium thickness from 80 to 10, crossing 40 and 20 nanometers. And what we observed, looking to the Schottky barrier height, is that for all the thickness from 80 to 20, the Schottky barrier height doesn't change. And this makes sense because the Schottky barrier height depends just by the surface. But at 10 nanometers, I observe a fall down of the Schottky barrier height from 1.2, that is the typical value, to the almost 0.9, that is really low. And I was looking into the IV curve, and okay, the Schottky contact seems to be really good. And again, this is the statistical distribution of the Schottky barrier height along the wafer. If I compare, this is our typical wafer with this widthness of the statistical distribution, and we have a value of 1.2 for the titanium. And for the titanium 10 nanometers, we got 0.93, as I said you before, with the same width. That means that along all my wafer is very homogeneous. That is a reproducible process that can be implemented also as an industrial one. So, but we were curious to look what happened inside my materials. So we performed some TM analysis. And this is the starting layer, the 80 nanometers one. So basically, there is my aluminum compound, my titanium 80 nanometers, and my substrate. And if we look to the surface between titanium and SiC, it's titanium, so it's 1.2, it makes sense. But there is a layer here that if we are going to look with higher images with THAM, is just an intermixing of aluminum and titanium because we are used to anneal this system at 475 degrees. So what we thought is, what happens if I grow just 10 nanometers of titanium and put aluminum on top? Aluminum should arrive at the surface. And this is the case because aluminum arrived there, it reacts with titanium. Here there is an higher magnification, and it forms titanium compound, and in a very homogeneous way. This is all crystalline, so very homogeneous, very good quality of my Schottky contact, and he showed a 0.9 barrier height. So just by changing the thickness of my Schottky metal, that in this case is titanium, so for the process flow doesn't make any effort, just manipulate that the sputter is not 80 but 10 nanometers. I lowered the barrier from 1.2 to 0.9. And the last is we are now interested on surface treatment because, again, Schottky barrier height is a matter of surface. So I just picked two papers, one from a Swedish guy that put on top of silicon carbide gold nanoparticle, and they observe a lower on the Schottky barrier height for this gold nanoparticle SiC deposited. And it's really interesting also because they can modulate by controlling the size of the gold nanoparticle. And this is a paper from our colleagues from Infineon in which they modify the surface by sputtering of argon on the surface, and they can again modulate the barrier height. And this, to me, is really interesting because it's not just a matter of process, materials, and design, as I said you, but also is a matter, again, of the surface. So this is leave a space in the room to develop new approach to obtain better performance on silicon carbide diodes. So summarizing, here are all the results that I showed you. But to me, the key message is all the time, maybe people think that just to change the design, just to change the materials. But to me, the more interesting result and basically the control, because it's not just a matter to lower the barrier, but just to control, because then depends again of the application, is the combination, as I tried to show you before, between materials and process, design process and materials, and again, process and materials. So this is what I would like to share with you. Thanks for your attention.
We're open for questions.
Do you refer to as deposited to? Do you refer as deposited to the titanium barriers which are 475 annealed?
Yeah, I mean, to me,
Okay.
is as deposited because 475 is the temperature to form the alloy, the aluminum alloy. So it's something that I can change.
Okay. And then, well, I don't know if you would answer, but is it as default condition that you don't have a sort of diffusion barrier between your titanium and aluminum? Is it?
Okay, no, there is no barrier because it's a one sputter process. So it's in one step sputter process. But again, for the 80 nanometers, that is the thickness that we are used to, there is no problem, as I showed you before. But what's good that there is no barrier for diffusion to get that system there. But you can just grow up a little layer of oxide, very thin, and it can act also as a barrier. If you grow just 2 nanometers, 3 nanometers of, or just leave the titanium to oxidize for 1, 2 nanometers, it doesn't change. It doesn't make any changement in the electric performance. We proved it, but it acts as a barrier for aluminum diffusion. So we are able also to control this.
Hi, so thanks for giving a nice talk. I'm Ashutosh from LICE. So I mean, in one of your slides, you have asked that on using tungsten carbide, when you heat at 700 degrees centigrade, you can change from 1.05 to 1.12 of electron volt.
Yeah.
And that's about 15%. I mean, would you like to comment on the device-to-device variation, or how many devices have you measured in reaching out?
You mean in the case of tungsten carbide?
Yeah, in the case of tungsten carbide.
Okay, so you are referring if it's an homogeneous process along all the wafer?
No, I'm just saying that you're commenting that it's from 1.05 to 1.12, so it's about 15% of the change or increment in the barrier height.
Yes.
So I mean, what is the device-to-device variation? Because it's the 15%, so how many devices have you measured to reach out that conclusion?
No, I used to measure on a wafer, so there are thousands of devices on a wafer.
Okay.
And the variation is 0.03.
Okay, so this is the average value you're talking about.
Yeah.
Okay, yeah, thanks.
Okay, we're a little bit late, so let's thank the speaker again.
Thank you.
The next presentation will be given by Hyung-Seok Lee from E3, and it's about recent progress on gallium nitride-based semiconductor devices.
Thank you, Mr. Chairman, for your kind introductions. I'm Hyung-Seok Lee from E3. It's a great honor to be here today to share all of you our recent progress of GaN-based semiconductor device technologies in E3. The content is following. I will introduce E3 briefly, and then I will mention about GaN device technology in E3 shortly. And more interestingly, I will talk about some GaN summon issues. And finally, I will summarize. First, general information about E3. E3 is one of the biggest government-funded independent R&D organizations. It was established for the ICT R&D in 1976. So we have 12 lab buildings in 300,000 square meters of Daejeon campus. Also, we have some other foreign French office in Beijing and in Silicon Valley. This picture shows our Daejeon campus pictures. I'm working on these third buildings and material and device laboratories. This slide shows E3 wide-bandgap device R&D histories. We developed gallium arsenide power MOSFETs and millimeter wave, the PMT device in 1991 and 1996 respectively. From the 2010s, we started the development of the gallium nitride device and silicon carbide device. Recently, we developed the Ka band power amplifiers and Ku band power amplifier too. So I will show entry facilities. So we have many labs in silicon labs in around 800 square meters size. So we are working MEMS and CMOS and the silicon carbide power ICs. And in compound semiconductor labs, so we are working on gallium nitride, gallium arsenide, and 35 millimeter wave and optical device too. And also we have some material analysis labs and packaging test labs. And for the frontiers device, we are working on the individual labs in the 3,000 square meter size lab size. So we do this many labs. We do 4-inch compound and 6-inch silicon, the full process for R&D and pilot productions. So I will talk about GaN device technologies. GaN is quite interesting materials. It has wide band gaps and it has higher critical breakdown field. And also to improving the thermal conductivities, we can utilize in the silicon carbide substrate. And also it has high saturated velocities. So also GaN mobilities enhanced with these HAMT structures for high gain and high frequency operations. So now I will talk about some 0.1 micrometers D-mode GaN HAMT MMIC libraries. This picture shows our 4-inch GaN MMIC library wafers, and this is the MMIC wafers. And this picture shows cross-sectional view of the 0.1 micrometer D-mode HAMT structures. The process flow is here. We are using the ohmic context. So using silicon ion implantations to increase the doping concentrations. And then device isolation by ion implantations. And to making some thin film resist formations, we are using TFR formation in the metals. And also we are using the T-gate. Here is the 0.1 micrometers gate length with the E-beams. Recently, we are developing 40 nanometer and 60 nanometer T-gate gate lengths. To making some MIN capacitors, we are using silicon nitride passivations and then top metals. Finally, we are using the air bridge metals interconnections. Here is to front the process floors. The other remaining part is to here, the backside via hole, the process to making some ground and then to reduce the thermal issues and also reduce the capacitance. I will talk about more. This picture shows internal backside via hole pictures. Here is a top view of the device. Here, gate, four gate, and this is a source, and this is a drain regions. The circle region is a via hole. When you get the cross-sectional view here, so we needed to making some very smooth the via hole process. So first we needed to the nickel platings to add some hard mask, and then we etching the silicon carbide selectively by the ICP, and then gallium nitride etching also by the ICP. And after that, we needed to 5 micrometer thick the gold plating here. And after that, we wafer separations, and then finally the chip sewing. Here is the result. Here is the top view of the device, 4 fingers gallium nitride HAMT device. And also we are using the load pulse applications. Here is to the D-mode power characteristics, around 32 dBms of powers. So I will go to the GaN power switching in the A3. The process of the gallium nitride power is quite similar with the RF device. Only the main different thing is we are using GaN silicon instead of the GaN silicon carbide. And also we using field plate structures to making some high breakdown here. And this is the fabricated 4-inch gallium nitride D-mode power FETs, and here is to gallium nitride miss FET diced structures. So after the fabricated device, normally we testing 100 or 200 device to check the leakage mapping. Here, sometimes it's happened to early breakdown, but most of the device is quite survived, and also it has very low leakage current levels, around 20 nanometers amperes at the 200 volt. So after the device mappings, we select the device and then packaging to making some E-mode device with the cascode configurations. We do one, the silicon low power MOSFET here as a gate functions, and then the others, so gallium nitride, the miss FETs for high voltages, the normally on the gallium nitride structures here. After that, we can operating the E-mode structures. It shows more than 600 volt high breakdowns and more than 10 amperes as current levels. So I will talk about some GaN summary issues. I talked about some gallium nitride, the switching characteristics and RF characteristics. GaN is handling high current and high voltages. But problem is it has a very high junction temperatures. Typically below the gate, around the surface areas, it has hotspot zones. Sometimes it happens to the more than 300 degrees Celsius. When you get the micro IR analysis, here is to very high temperature areas. So what happened to when we increase the junction temperatures more than 300 degrees Celsius? So we can look at the graphs. The typical junction temperature is less than 150 degrees Celsius, but the lifetime is 10 to 6 hours. But when we increase the junction temperatures, the lifetime is dramatically decreased, 10 to 3 hours. So lifetime is influenced by the junction temperatures. To solve these problems, so we are typically using the silicon carbide with a better thermal conductivity substrate. So some groups using the more aggressive approach with some diamond substrate. It has a 5 times higher thermal conductivity comparing to silicon carbide. So I will compare with the Canon silicon or Canon silicon carbide versus Canon diamond. It has some trade-off. Canon silicon advantage is the cost of the substrate. Also, we can utilize the 8-inch substrate or 12-inch substrate. But problem is to high junction temperatures and need to additional cooling component. While the Canon diamond is lower operating temperatures, making the small size, better reliabilities. But problem is to the cost of the diamond, and also handling Canon diamond is very tricky. So when using the Canon diamond, junction temperature is the best. Canon silicon is the worst. The Canon silicon carbide is a medium value of the temperatures. So we compared it with the Canon silicon and the Canon diamond. So nominally, these two structures is the same epitaxial layers, except of the silicon substrate and the diamond substrate. So after the fabrication of the device, we measure the output characteristics. One main different thing is to drain current levels. Canon diamond is higher drain current compared to Canon silicons. And the other one is to suppression of the self-heatings. The Canon diamond is almost constant, but Canon silicon is a very strong self-heating effect. So we extracting the thermal resistance with some increasing the choke temperatures and measure the drain current powers. So with these graphs, we can extract in the thermal resistance. So Gannon silicon is 10 times higher comparing to Gannon diamond thermal resistance. So this is the reasons why the very strong self-heating effect and also lower drain current levels. Also, so we measure the IR images to check the junction temperatures. This is the IR image setup here. And this is the chocks. We keep the stage temperatures around 70 degrees Celsius to get the reference images here. This is a result of the Gannon silicon and Gannon diamond FETs. Without bias, Gannon silicon and Gannon diamond is a similar, same temperature, 70 degrees Celsius. But after bias on, the drain voltage is 35 volt. The Gannon silicon is 200 degrees Celsius in here, hotspot zone here. But Gannon diamond is dramatically reduced the junction temperatures up to 82 degrees Celsius. So now I will talk about some another method to managing the thermal issues. GaN diamond flip chip the packagings. The idea is these high temperatures happen to near the surface. So if we using the flip chip bonding, so with the very high thermal conductivity, like some polycrystal diamond, we can reduce the high temperatures. So when we look at the simulations, simple simulations, the Gannon silicon typical GaN packaging shows 180 the junction temperatures, but GaN diamond flip chip shows 140, around 40 degrees Celsius difference. So to compare with these two structures, we fabricated GaN SCBD, the BPOA process floor. The process floor is the follows. This is similar with the GaN FET process floors. One main difference thing is we are using bonding pad over active here. So we using the more than 5 micrometers gold tin the metal, and this is to fabricate the 4-inch ethylene GaN SCBD, and this is to BPOA structures. Also, we have some 65 micrometer gap to protecting the short and the cathode and the anode, cathode and anode here. So I will talk about some flip chip process. So we are using the FinTech flip chips bonder here. This is to dice the GaN SCBD, BPOA chips. And the upper stages, it has some GaN SCBD chips. And lower stages, so PCD with the metal pad. With these flip chip bonders, it can chip and the PCD alignment, and then press and the heat. And then finally, we can get the GaN flip chip on the PCD here. And to compare these structures, we are using the TO packages here, GaN diamond flip chip bonding, SCBD TO package, and the typical GaN SCBD chips. And also we measure the IR thermal image. Here is we fix the positions to get the reference images. Here we can see the silhouette. This is cathode and anode, and this is a metal pad without bias. And after bias, around 5 amperes, so typical GaN packagings shows 170 or 180 degrees Celsius. Also, we can see quite rainbow colors here. It means about some different temperatures, and also it is different current flows because of these wires. While the GaN diamond flip chips here, we can see the quite constant colors like some green colors. And also it shows 130 and 140 degrees Celsius. It's around 40 and 50 degrees Celsius difference. So of course, we can see there is some the red spot zones. I think this is void of during the flip chip bonding. The final approach, we are using gallium nitride laser lift-off techniques. Laser lift-off technique is quite a typical method in the LED areas. So we did some 190 or 240 nanometers laser pulse. We are melting the gallium nitride, and also after that we can get the thin gallium nitride epi layers. So with these ideas, we are trying with the GaN-HAMT to process with the LRO. The first, we are making some RF GaN-HAMT device here. And then we do some PCB wafer bonding. And then we remove the sapphire substrate. And then we are just adding aluminum substrate with the bonding metal or copper film plating. After that, we remove the carrier wafers and the PCB. The copper film and the aluminum nitride thickness is quite similar with around 500 micrometers. Here, so we can see GaN aluminum nitride LRO package is quite flat. And the other one is the GaN coppers LRO packages. It has a high board because copper plating is a very high thickness, around 500 micrometers, the thick the coppers. And this picture shows transport characteristics and output characteristics. And we can see the GaN sapphire substrate has a strong self-heating effect and lower drain current. And the better aluminum substrate here, around 40% improving. And the best one is to copper plating. And also it has a very constant and also suppressions of self-heating effect here. Also, we measured the RF device technologies, device characteristics, and around 20% or some 15% improvement. This is not the dramatically improvement comparing to DC. So I think we are adding metals bonding pad with this aluminum nitride. It can increase the capacitance. Okay, I will summarize my talks. Gallium nitride is quite ideal. We just shows gallium nitride RF and MMIC technologies and can high power switching device technology in ETRI. And also I will describe about how to manage GaN thermal issues with high thermal conductivity spreaders for next generations RF and power device. GaN diamond is the best for the mass productions, GaN PCD flip chips, and GaN aluminum nitride, or GaN coppers with the LRO is possible. Thank you very much. If you have any questions, please let me know in send the email for this address. Thank you very much.
This was the last presentation in this session. Now we have a coffee pause for 20 minutes and hopefully we start on time at 15:50. Thank you.